Okay, so hey
Alrighty.
guys, this or presentation, I guess, is going to be about quantum computing and its history, development, and potential. Um, oh. So I guess the overall objectives and overview is number one. Well, we're going to introduce myself, but outside of me, we're going to go through the history of computers and I guess why we need something new. Two, the base physics and how quantum computers exactly work, and three, the problems they solved and its applications, as well as the problems we have trying to build one. And so I guess, who am I? I'm Jacob Mozdzen. I am a computer science and physics dual degree. So fun fact, I actually came in as physics and I worked at OIT, and I still do, but like 80 to 85% of the people there were all CS majors. And so they brought me over, but I'm still physics. And so I really like the physics side of things. But in the future, I see myself as like, hopefully a software dev. I just do physics because I like really enjoy it. I'm a junior. I'm going to be a junior, and then I'm in the band, and there's my little section. We're called the Faltos. So there's a cute pic. But anyway, on to the actual presentation. So see, these are some of the milestones that I think that are really important in computing. And so there's a lot of them, but these are just the ones that I picked out. And so these are kind of, again, from the mechanical side of computing to electrical components and then on to quantum mechanics. So we really kind of start off way back when in 1822. To 1910, and we get the first mechanical computer. And so the first mechanical computer is actually designed, but it's not actually fabricated until the inventor's son comes around and actually built it 100 years later. That was really kind of like the first stepping stone of building an actual computer, using mechanical parts and having it do things that we wanted to, like math and arithmetic and actually solving problems. And so later on, we come around into 1943 and we get the first electronic computer built, which is called ENIAC. And so this is kind of really the foundation of where we get computers from. It kind of lays out the ground base work for what an electronic computer is, and it gets better every single time. But one thing to notice again is the year 1943. So again, it's during World War II, and we can see that computers were always built to solve problems. And so the problem was that during World War II, when planes flew and ships were in the water, they would need to throw artillery. And so they would have these advanced complex lookup tables. And so they're, go.
What is this on that movie? What's it called?
No. So this is actually, I don't know what the movie's called, but that computer came out 2 years before, and it's not actually considered a computer for some reason, which is kind of like bogus. But anyway, this is like
that's so weird. Why didn't they consider it a computer? That's so
I don't
weird.
know. There's some like weird specifications that it doesn't like match up, so it's not actually a computer.
Okay, interesting. So so Turing didn't invent the first computer. That's like what you're telling me.
No, I mean I think it was a computer, but like I guess like definition wise, it's not really a computer.
Weird.
Yeah, okay. I think his was in 1941. But I think this was like the first reprogrammable computer. And so what they would do is, instead of looking through these like long lookup tables of values, they would just kind of like type in the wind and I guess how far the ship is. And so it would do all these calculations and lookup values. And I guess it helped solve a certain problem. And so this is really kind of like the stepping point of where computers start to come along. And so in 1947 to 58, we see major strides toward the modern computer. And so these are really toward their hardware. So in 1947, we invent the transistor, which kind of replaces the mechanical relay. So before then, we still did read computers in binary, but we used mechanical switches. And so mechanical switches have weights, and so it takes some time, and they're not as effective, and they break, which is sad. So we built the transistor, so all is good. And then 1958, we came along with the integrated circuit. And so it later won a Nobel Prize, but I guess the real issue with the computer before then was it was too big and clunky and it broke down a lot. So they tried fixing this issue. So they came out with new technology to kind of make the parts smaller and more effective, and they broke less. And so these are kind of the things that are still being built into your computer today. So with some real good work. And so again, this is toward the hardware. And then in 1973, we come around. And so computers have been out for a while, but they're not really, I guess, easy to use. And so we have all the parts and we want to introduce it to the public. But the problem is it's not going to be used if it's not easy to use. And so in 1973, the first GUI was introduced to the public. So it took the computer, which was, I guess, a very scientific thing, and it made it open to the public in a very easy sense. And so that's when we kind of invented software, like more software heavy sides. and bringing the public into these computers. And so most recently created was in 2016, we created the first reprogrammable quantum computer. And so computers are great and all, but sometimes we need to take a step back and reevaluate how the computers work to build a better one. So that's exactly what was done there. So these are just a few of the milestones which I think were really important in building the computers that we have today. And so we can see here are, here's a basic slide of what the first actual computers were. So if you actually, I guess the definition back then of a computer was someone who does arithmetic, and it wasn't actually really thought of as a computing device. So for a long time, humans were actually declared computers. And so eventually what the problem was humans aren't that great at multitasking. So they created something called the abacus, which was really good at doing simple math that was easy for multiplication, division, adding, subtracting, that actually came out like 4,500 years ago. So this was way back then. And so it solved the problem that humans were not able to, I guess, keep all these mental additions and subtractions and multiplications in their head. And so while this was great and all, we actually needed something better. So that's when the step reckoner came along a few hundred years ago. And they said, well, if this is so easy, why don't we just make it into a machine? And so, which is actually what they did. And so before, the mathematicians were really kind of doing all this arithmetic, and this guy came along and said, why don't I just make a machine that does it for me? And then he said, if I can just make a machine that does it for me, I can give it to a peasant and he can do all the arithmetic. Well, I can actually give the mathematician like some real problems. And so that's when we first started actually building these mechanical machines. And so they kind of replaced the abacus. And so later on, we create the analytical machine, the analytical engine, which really does the same thing this does, but on a bigger and wider scale. So the step reckoner was able to do, I think, multiplication in like 3 minutes, which is great, but like 3 minutes is a long time for someone that can just do it itself. So this guy over here was able to crank it out. And then one of the also really handy features of this was that it was able to be reprogrammed. And so it solved a lot of issues in that you didn't have to build a new machine every single time you wanted to solve a problem. And so these were all great and all, but what really came to the advent of the modern computer was electrical components. So I guess the breakthrough that I see here is that we started using electrical components. And so this increased our computing speed. They broke less and they took up less physical space. So again, like I said, all these computers before actually did use ones and zeros and binary, but they had to use mechanical switches like this one. And so there was about, I think, 3,000 at least of these mechanical switches, which were kind of clunky. They're like that big on the machine. And so again, every time it moves, it gets a little rusty or broken down. So every day you'd have to replace a different part, which was kind of gruesome. So what they ended up doing was they created the vacuum tube. And so the vacuum tube it was smaller, more effective. There wasn't as much moving, and it was able to work, I think, 50 times faster than the mechanical switch was. So already we see like a huge increase in computing speed right here, and it's smaller. And so we go on to continue to create the transistor. And so the transistor actually doesn't have any moving parts, which now we don't have any wear and tear. We don't have to replace these parts. It takes up less space, and again, faster. And so later on, we created with the integrated circuit, which just holds hundreds of millions of these transistors inside of it. And so all these are great. It's speeding up our computer, but now we run into our next hurdle, which is size. So if we keep decreasing, making these transistors smaller and smaller and smaller, at some point, they become smaller than atoms. And so this is kind of where Moore's law comes along. So Moore's law says that every 2 years, we should double our transistors in our computer. Well, eventually we reach a certain point where we can't shrink our transistors anymore because they're so small. And at this small scale, if you go too small, eventually these, I guess, atoms will start to quantum tunnel and just actually like leave the circuit altogether. So it doesn't really do anything for us if we don't have a working circuit anymore. So our next current hurdle is physical size. And so that's where the...
what do you mean by quantum tunnel, Jake? Like...
So let's say I have a wall, okay? And I have a particle right here. If the wall is not thick enough, the particle can just like go right through it and just like appear on the other side.
Okay, so essentially the particles weren't doing what they were supposed to anymore if it gets too small. Like they'll mess with each other.
They'll just like hop on everywhere, and then we don't have, because they're hopping on everywhere, we don't have a current anymore because they're not actually following like what it's supposed to do. So let's say we had a closed current, because let's say we set up a wall and there's a closed current, and then this atom's like, nope, and it just like jumps over and it opens the current. Well, then like there's no point of the computer anymore. So at such small scales, like we can't really apply what we classically know, and we have to kind of rethink the way we design the computer. And so that's where the quantum computer comes along. So what the quantum computer does is it actually tries to work smarter and not harder. So the quantum computer takes a step back at computing and it says, how can I work smarter rather than trying to make my components smaller and smaller and smaller and pack more and more and more? And so what they came up with was actually using a qubit. And so quantum computers use this idea of a quantum bit. And so on all of our computers, we have the classical bit, which is just a 1 or a 0, an on or an off. And so that's how logic design works. So we build these complicated circuits that just basically are just ons and offs over and over and over again. And so they can only hold one state, either an on or an off. But what the qubit takes advantage of is something called superposition. And so superposition basically means that something can be in more than one state at a time. So we can see this qubit right here. So instead of just being a 1 or a 0, it can be anything along this curvature. So a lot of the times when we talk about qubit, we say that it can be like 50-50, so 50% 0 or 50% 1, 90-10, 40-60. As long as they add up to 100, we're good to go. And yeah, and so what quantum computing really takes advantage of is eventually, now because of this, instead of holding 1 bit of data, we hold 2 bits of data, or I guess, yeah, 2 bits of data for every 1 bit. So now we can double our computing power. And so that's what quantum computing really takes into its core, is it's able to compute more harder problems with, I guess, less bits. So it can really take advantage of this kind of exponential addition of 2s with a qubit. And so these are just some examples of like what the quantum computer looks like. It's not your average computer. But now we go ahead and talk about the next generation of computers. And so I say sort of, and so while quantum computers are great, they're not going to appear in our laptops anytime soon. And so why is that? And the first thing is quantum computers aren't slow, but they aren't fast. So we train classical computers to go as fast as they can. We constantly try and make them go faster and faster and faster, which is great and all, but we're not trying to make the quantum computer go fast. We're trying to make it so it can compute more things than a classical computer would. And so on top of that, it's not going to solve every single problem you want it to. So if you wanted to do 5 times 3, I wouldn't hop on a quantum computer and go 5 times 3. Like our classical computer is good enough for that. Or like printing hello world. Like I wouldn't go on a quantum computer for that. I would just do it on a regular computer. And so a lot of that holds true. So a lot of what we see in the future in software development is still going to remain on these classical computers, but rather we're going to tackle larger certain problems like optimization, simulation, and things of that nature with a quantum computer, because again, it's a lot better. And so something I like to, I guess, make a similarity between is a CPU and a GPU. So usually computers have both, but you don't exactly use your GPU for everything. Like you have your CPU does a lot of work, but if you need that extra muscle power, you give some to your GPU. And so I like to think of it in that sense. So our classical computers are staying, but in a lot of sense, if we ever need to do that bulk work, we're going to give it to the quantum computer. So it's just there as an addition rather than a replacement. And so on top of that, we have a lot of engineering obstacles to go along the way. And so, like I said, like the first reprogrammable one was built in 2016, so we still have a long ways to go. And so regardless of this, they're still pretty cool. And for the fact that they use a fundamentally different way of thinking than regular computers do. And they use the principles of quantum mechanics. And so really we're going to be talking about 2 main things in quantum mechanics today, which really kind of help with the quantum computer, and that is superposition and quantum entanglement. So I guess the whole entire magic of quantum computing. So this is where we get into the entire physics of how quantum computers work and where they came from, I guess. So back in the 1800s, there was this argument of whether light is a wave or a particle. And so in certain experiments, it behaved like a wave, and in certain experiments, it behaved like a particle. And so scientists were like, well, which is which? So they came up with an experiment. It's called the double slit experiment. So what they ended up doing was there were 2 slits, and so they shot things through each of them. But that's just the overall gist of it. So let's just pretend, ignore the light right now. Let's just pretend this is water. So every time we dip water, it creates these ripple effects. And if it were to go through these 2 slots, it makes common sense that would create 2 more ripple effects. And so if there's constant ripples, they constantly interact with each other. And so we can see that where they overlap, they can create a bright spot, and where they don't, they can create a dark spot. And so we get this kind of wave interference. And so this is really important to know that some things travel as waves, again, like ripples. So it makes sense that these kind of establish this interference pattern, because it wouldn't exactly make sense for this entire thing to be remain equally, because they all kind of overlap again, like I said. And so next we get into, we kind of redo this experiment, but instead of thinking of like water and wave as something that's fluid, we think of something solid and matter-like. So let's replace the water with a bucket of sand. And so we have this bucket of sand pouring on top of the left and the right slit. And so we asked, well, which one is it going to go through? Obviously, common intuition tells us that, well, it's either going to go the left one and the right one, which is what we observe. And we can see that the particle just chooses left or right. I mean, at the bottom, we can see that there's 2 stacks of sand, which is, again, to be expected. And so now we get into where things kind of get murky, I guess. So let's say there's this cannon that shoots out particles. And so we have this double slit again, but this time we're going to close off one of the slits. So we go ahead and shoot the particle. And what we expect is, again, because it's a single particle, like it's a piece of matter, just like the sand, but smaller, it's going to go through one of the slits. And so since this one's closed off, it's just going to go through this one. And so it's going to create, again, this pattern where all the particles end up. And we can see that there's like, yeah, there's this thick line, but there's some off to the side, but it can just be the particles like bounced off the wall or something. And so there's nothing too crazy about this. The particle just shoots right through the slit. And so now we have 2 slits. So does anyone want to take a guess what this will create? Again, we're still shooting particles, so.
Does it maybe like make still one line or something?
Yeah, so that's where scientists thought what would happen. So what we think is going to happen is it's going to shoot out over here. It's either going to go through the left or the right one, just like the grain of sand. The grain of sand can't go through both of them, so it's just going to pick one of them. But we actually see it creates an interference pattern like a wave. So even though it's one particle going through this, it creates a wave effect. And scientists thought like, this is funky. Like, this is not going to work. Like, we shoot a bunch of particles, which are like sand, and somehow they create waves with each other, even though, again, they're particles and not waves. So they're like, I'm going to outsmart this experiment. So what they end up doing is they start shooting particles one by one. And so they figure if I shoot it one by one, there's nothing for it to interact with. So before we had the waves would go through. And since there's constant waves, they constantly have something to interfere or to interact with each other. So they'd go like this and interact. But if they shoot one particle at a time, there's nothing for it to interact with, right? So it shoots the particle, and so we see this initial pattern one by one by one. And so with more times, we kind of see this interference pattern. And at the end, we get this, again, this interference pattern. And so this is where the mystery of quantum mechanics kind of lies. So like, no one can exactly explain why this happens. We just know it does, and there's mathematical equations to model this. If you can explain this, like, you win a Nobel Prize. But what we actually see right now is that what ends up happening, believe it or not, is the particle shoots out, and what it does is it goes through both of them at the same time, much like a wave. So it actually, it doesn't physically split, but like metaphorically, it splits into 2 waves. And so much like the wave ripple, it interacts with each other and creates this pattern. And so if we repeat it over and over and over again, we reach this final state. So it acts like a wave. So there's a 50% chance it goes through this one and a 50% chance it goes through this one. And that's where we get the idea of superposition. And so you're asking, well, how can matter do that? Because that's only for waves. So fun fact, everything behaves like a wave. So like I'm technically a wave, but the larger mass you have, the smaller the wave you are. So because like I have so much, like human beings have so much mass that our wavelength is, or I guess our amplitude is like smaller than like a millionth of an electron. So like there's no point. But down at these levels, particles both act like waves and particles because they're so tiny. But anyway, scientists decided to take this a step further, and they're like, well, I'm going to trick this. I'm going to see which wave or which slot it actually goes through, because it doesn't make any sense that it goes through both of them. It has to go through one of them. So the moment they started measuring it, so they added like a little light detector, or I guess like a photon detector, to see which slot it goes through. So does anyone want to guess what happens now? Now that we added a little motion detector to see which slot it goes through? We're still shooting particles.
Both of them.
Okay. No. So now that we measure it, measure which one it goes through, this kind of wave effect collapses. And so now it chooses which one to go through. So now it only acts in a state of the top, the left one or the right one. And we can see that like before, if we get the same setup, we got a wave-like interference. So that means the particles are acting like waves. Whereas now when we start to measure them, we actually get a particle-like setup. So merely the fact that we're measuring them changes the state they're in. And so this kind of is the basis of quantum computing. So like we take these qubits and we entangle, or we make them a superposition. So pretend this is a qubit, it's gonna go through both states at once, and it's gonna stay in those states until the entire time. And so once at the very end, when we actually measure our results, we measure it like this with this motion detector, it returns back to a 0 or a 1.
Wait. Pretty sure Jacob and I are on the same wavelength here, but why, when you measure it, does it decide that it's going to do the thing?
It just collapsed. So in superposition, when you're in a superposition, you're in a waveform. And so measuring the waveform collapses it for some reason. Like it just does. Like
really? Okay.
if you figure out why, you win like a Nobel Prize, but like you just have to know that it does.
Wow.
So we have this motion detector right here. And let's say we just like turn the motion detector off. Like it's still right here, but it's turned off.
Mm-hmm.
So now we get the pattern we saw over here again. So it's not that there's a motion detector there. It's the act of physically measuring whether it went through or not, collapses the waveform, and it turns back to a particle-like behavior.
I'm amazed. I have no idea how that can happen.
I know.
Yeah. So again, so like classical computers like 1 or 0. But what quantum computers do is they shoot it out. They don't measure it until the very end. So at the very end, we get 1 or 0. But now, because we have 2 states, we can do a lot more work with just 1 bit of information. So that takes us into superposition and the power of 2. So here are 2 qubits in this example. So we have first qubit, and it can be 0 or 1 or both. And this one is going to be 0 or 1 or both. And so we're going to put them both in superpositions. So that means this first qubit's in a state of 0 and 1, and the second qubit is in a state of 0 and 1. So over here, remember back to discrete math, and we had like truth tables. So now, rather than, I guess, looking through the truth table to see if this is 0 and 0, 0 and 0, this truth table actually represents the entirety of this one run. So in classical computing, if we wanted to run this value, we would need to if we wanted to run each one of these values, we would need to do 4 computations. We need to do a computation of this one, 0, 0, 0, 1, 1, 0, 1, 1. What quantum computing does is it does all of these at the same time. And so one thing to note is, even though it does all of them at the same time, there's only one output or result. And so that's where probability comes into play. So we can do different math on these to determine what probability they are. So let's say we have this truth table right here, and we run it 1 time. So our one result is going to be 0, 1. That doesn't necessarily mean that like our answer is 0, 1. It just means we got that 1 time. And so what we actually have to do is we have to run these scales thousands of times to get accurate results, because the more times we run it, the more times these probabilities are true. And so I'll talk more about that later on. But we can see that because this is in a 0 and a 1 state at the same time, they have two states rather than just 1. And so we notice that if we add a third qubit, the third qubit acts on qubit number 2 and qubit number 1 at the same time. And so we get a doubling. And so really cool, because now we double our entire truth table every single time we add 1 qubit. And so we can see that this power grows exponentially. So if we have 5 qubits, we can do 32 simultaneous simulations at the same time. And one thing to always make sure of is your probability is always going to add up to 1 at the same time. And so if we add a 4th qubit, again, so now we have 8 probabilities. If we add a 4th qubit, because this is in 2 states at the same time, it interacts 2 times per each qubit. And so now we get 16 states. And so superposition, when I go back to quantum volume or computation volume, it allows us to compute a lot more volume per run. Any questions on that one? Okay, so then our second fundamental thing in quantum mechanics is something called entanglement. And so what we're allowed to do is, let's say we have two separate particles, we can actually entangle them together so they act, what I do to one, I do to the other. And so they can be any distance apart, like it says right here. They can be across the entire galaxy. But as soon as I do something to one of it, it does something to the other one too. They're just entangled. We don't know why. We've tested this multiple times again. It's just something that exists and we know how to reproduce it. We just don't know exactly why they're entangled, I guess. And they have effects instantaneously. So let's say we're on opposite ends of the universe and I measure one of the particles, its waveform collapses and it instantly turns into a 1 or a 0 or whatever state it's in. But the other particle too instantly collapses at the same time. And so one thing we learned about in physics is that nothing can move faster than the speed of light. But if you have something moving instantaneously, of course it's faster than the speed of light. And so now we have a question of how can something move across the exact galaxy with information that's faster than the speed of light? And so really the way we need to think about this is that there's no actually information moving between the two particles. They're not communicating, they're just entangled. Think of it like a math problem. So both of these need to add up to a 0. So one can be positive, one can be negative. And the moment we measure either one of them, the other one's automatically that state. They're in a constant flux, I guess, of states, and their constant flux of states is related to each other. But yeah, I can see you have a question, Kendall.
I was just like relating this back to like Schrodinger's cat, like where it's like you don't know it's both dead and alive before you open it, and then you know its state, like it's either dead or alive when you like find the cat.
Yeah.
Okay.
So that's superposition. So the cat's both dead and alive, and
Yeah.
then it exists in both states while the box is closed. And the moment we open it up and we measure it again, this waveform in alternate reality collapses, and so now we get it's either dead or alive, and in the binary sense, it's either 1 or 0. And
but so, you're saying that these things collapse on the opposite side of the universe. So it's not like we just know that one's a 0, so the other one automatically has to be a 1. You're saying that it physically does action?
Well, it doesn't. No, there is no action. So they're just revolving around each other. So like, let's say the one on the left right here. Can you see my mouse?
Mm-hmm.
So let's say this one's a 0, or so let's say this one's a -1. This one has to be a +1, and like switch them around. If this one's a +1, this one has to be -1.
So it just becomes known when.
Yeah, it becomes known.
But they are related. Okay.
Because they always have, when we entangle particles together, they have to be complementary to each other.
Okay. But why how do they actually get entangled?
So that's for later on.
Okay.
Okay, go for it, go.
Are you able to change the state or no?
Yeah, so if you manipulate one, you manipulate the other too, because they're entangled. So whatever you do to one, you do onto the other until you measure it. Then it breaks both of its, I guess, waveforms, and they instantly become like 1s or 0s and vice versa.
So how can you change it then if you're not like measuring it?
Well,
like, how do you know you're changing it?
Okay, so that goes back into this one. So like in this table right here, we have probabilities, and so we can manipulate their probabilities. So like, let's say I do like, I don't know, I can change a certain probability that this state is going to be more than the other one. Actually, okay. So in logic design, we have and, or, not, all of those gates, right? So we can't apply those onto these. We need special quantum operations. And so these quantum operations, there's like 5 main ones. There's a Hamburg, there's like a C0, a not. And so all these operations are reversible. So when you apply one of these operations onto the qubit, it changes its state. So like, let's say we applied something on the third one. That changes like the third probability. So when we go down the list, we actually have to change every single one of these qubits or every single one of these probabilities, because every single one of these has, it's interacting with a third qubit. So what we do onto one qubit affects every single one of the other ones, and that affects their probability, but they always in the end have to be 1. And so when we measure it, again, it can end up being any of these, but again, like it can, if we measure it, it can end up being the 0.2% probability over the 83% probability. So like, we don't know the outcome until the very end. And so that's why we have to run like 8,000 operations on this to determine that, okay, this one's the clear majority winner. This one should be happening.
That's really, Vinny had his hand raised.
Oh, sorry.
No, it's all right.
Go for it, Vinny.
Oh, no, it's totally, you just answered the question.
Okay.
Yeah.
Okay, yeah. So those are the two main things which kind of like determine how a quantum computer works: superposition and entanglement. So now we talk about the decoherence, and so this is really what kind of makes it hard to build quantum computers. Sorry, I really like to use emojis, so I made emojis. So the one rule is that if we want a quantum system to exist, we need to put it in a happy state. And so the two rules we need is it needs to be really cold, because we want, particles are not naturally in a quantum state. They're not naturally 0 or 1. They like to be definite. And so the only way we can establish this is when we make it really cold, so cold that it's near 0 degrees Kelvin. It's like 0.00015 degrees Kelvin, which is like insanely cold. And it also has to be in a vacuum. There was no vacuum emoji, so I just put a broom. And so the system, qubits can't really interact with anything else, because if it interacts with anything else, there's another force on it. And so again, that means there's something interacting on it and it's measured. And so the system decollapses again. And so this is kind of, we see if it's, the two main issues right now is in a vacuum and being cold. So if it's both in a vacuum and it's cold, like just like Schrodinger's cat, it's both dead and alive. And the moment it decoheres, so that means if it's no longer in a vacuum state or it interacts with something it shouldn't have, or that the moment that it reaches 1 degree Kelvin, then the qubits immediately break and they go into a state of alive or dead. And so again, like here's a nice little example. So in classical, everything's kind of very concrete. We know it's a 1 or a 0. In quantum, we get these wavy lines to represent the waveforms in superposition. So here we have like a dead cat and a live cat, and the road's no longer a straight path, it's curvy ups and downs. And so that really is kind of what defines this principle. So now we're going to do an example. If I can just, okay, I can't exit out. Okay, there we go. So what's actually really cool is that IBM has an online quantum computer. And so I'll actually show you guys. They have all of these quantum computers out there in the world, and they're free for anyone to use. So you just go online, create an account, and you can actually make quantum circuits and run them on quantum machines. So we're going to go ahead and run, let's create a new one. And so another thing to note is there's actually 2 ways to create quantum circuits. So we can go down the composer route. And so this is how we build literally like circuits like in logic design. And there's the Nesquik notebook, and so that's written in Python. But essentially what that does is it's, this composer is actually just a GUI for, I guess, the notebook. So the notebook does everything this is, but just a not visual representation. So this one right here gives us 5 qubits. So we literally have 5 qubits to play around with. And so these are all the different gates we have. So like I said, these are the these are like the and, nor, not. And so to begin, quantum computers are always kind of, or I guess like quantum notation is there's these bracket notation, and these are actually vectors. So a 0 vector is a vector of 1, 0, and a 1 vector is a vector of 1, 0, or 0, 1, because we're in both states. So to initialize it into superposition, we apply something called the Hagenberg state. And so this makes the first qubit, or qubit number 1, and it makes it into a superposition. So it's no longer in a state of 0, it's in a state of 50-50. And so something cool we can do is we can apply this gate right here, and it's essentially like an if statement. So it says, if this is a 1, or if this is in superposition, do the same thing onto here, and vice versa. And so now what we're going to do is we're going to go ahead and collapse these. And we're going to go ahead. Okay. I cannot spell. So something really cool is like, we're literally going to, I guess, create an entangled particle in this. So we're going to go ahead and say these changes. And so like I said, first we're going to go ahead and run it on 1, just so you can see. And we'll just do it in the simulator for now, because there's a lot faster results. So it went ahead and it's completed now. So now we can see like I said, so here's our state, and we get one result, like I said. So that's great and all. So it gave us one probability, but there can be a total of 4 probabilities because, again, each one is in a state of 2. And so it only gave us 1, and that's because we only ran 1 test. So like I said, if we want a more accurate representation of what it actually is, we need to go ahead and run 1,024, 4,000. And so the higher up you go, the more accurate to real life it is. So you go ahead and run it a few seconds ago. Okay, it's running. And so now we can see that there is literally a 50-50 of each. So it essentially just measured the states. And so it said, go ahead and measure both of them and see what comes out. And so they both actually appear. So we can see that there's 0, 0, and 0, 1. And that means they're both equally as probable. So they're entangled. And so that's like great and all. But we just did a simulation of it. We didn't actually run it on a quantum computer. So let's go ahead and run it on one of them. So we'll go ahead. And so now this request was actually just sent to London into IBM's quantum computer. And so, okay, we're in a queue of 5, but it's loading. Actually, I think I have one that's saved.
Do you play on here often? It looks like you have quite a few tests.
Well, I just discovered. Okay, so here it is. So this is what it actually looks like on a quantum computer. So like I said, all 4 states are represented, but that's not necessarily something we want. So you can see that we didn't actually do anything to the 2nd or the 3rd state, but so we actually didn't want these 2 states, but like I said, there's a lot of quantum error when we run these things because of decoherence. So a lot of our results aren't going to be exactly what we want them. And so this is the reason why we oftentimes run 1,000, 2,000, 8,000 runs, because the more often we run it, the higher probability or the more accurate these tests are. And so we can see that 50% of the time we reveal this one, and 50% of the time we reveal this one because they are entangled. So they have an equal chance of appearing. So that was the entanglement one. And so that's it for now. We'll come back to it. And so now we're going to go ahead and talk about its applications. Sorry, I think my computer's going wild. I'm not sure if you can hear it. Okay, so now we talk about the applications, which are pretty cool. So quantum computers are really cool, but again, they're not the one-all, like the 1B solve all. They're really good at solving certain problems like optimization. So there's a really, I guess, famous problem in this category called the salesman problem. And so essentially what you do is you have a number of cities, and so you want to determine the most optimal route to get from city to city to city. And so here it lists the possible routes. And so you can see that 5 cities like cool, 10, like it jumps a lot from 12 to 181,000, 20 double again. So literally with 25 cities, 25 places, you can see that there's literally 3.1 times 10 to the 23rd possibilities. And here again is a formula. And so we can see why this would be, I guess, an issue for companies like FedEx or Amazon when they need to deliver things and find the most optimal route between, I guess, house to house to house. And so again, what this allows us to do is we have these massive time jumps. So you can see that for a classical problem, if it's a big O of 2n, in the quantum, it's represented in a big O of n time. In some classical cases, a big O of n is represented in a big O of square root of n quantum time. So we can see that this quantum computer can do massive crunch time on these big numbers. So it's a real push forward from those companies to try and reduce travel time, traffic, costs, and find the most optimal route that way. Another big area is chemistry. And so the pharmacy field is always trying to, I guess, stimulate and find new medicines. And so recently, I guess the largest model ever recorded was BeH2, which is like really sad because like if you think about it, Be is like the 4th element and hydrogen is the first element, and they only managed to stick 2 hydrogens onto a beryllium, and that's like the largest they could model. And so a lot of that really is hard because electrons you don't know where electrons are. They behave in a quantum cloud, and so you have to, I guess, simulate this quantum cloud, which is really hard to do. So again, it's really hard to simulate all these repulsions coming from every single electron where there's not one definite place for an electron, rather it kind of exists in a superposition inside the cloud. So you don't know exactly where it is. And so it's really hard to model on a classical computer. So that's where quantum computers come along, and they make it significantly easier. So this has potential in the pharmaceutical industry. And again, we have like massive speed up times. Anything we want to model exponentially in like the classical sense is now linear time in quantum, which is like mind blowing. Like that's so much faster. And like a lookup time of n is quantum time of like square root n. So like let's say we have like 10,000 items, a quantum computer can like go through all of them in like 100 queries, I guess. And so I guess the most famous actual model, or the most famous application of quantum computing is called Shor's algorithm. And this is kind of an encryption based algorithm. So essentially how encryption works is, I guess in today's eyes, we use RSA. And so that's a lot of, they use factoring of numbers. So it's really, really hard for computers to factor large numbers where there's only 2 prime factors. They like, it can't do it. Like for 1,000 numbers, like it'll take like years and years and years. And so it's like really pointless. So we use this a lot when we use like online credit card purchasing, like when we want to send encrypted messages. We use this technique of multiplying these 2 primes together and like getting this huge number. And so it's really hard for computers to decode these like massive numbers. And so what Shor's algorithm does, it actually uses like a clever implementation of this. And so by using superposition, we can actually line up there's no like easy way to explain this. So we have like a wave, and so it can pick certain frequencies, and those frequencies actually are the factors. So it can pick out those factors and try them all out. And so it takes something that's an exponential time with n. So it'd be like e to the n time. And now it makes a polynomial. So it's like a big like jailbreak hack to like breach security. So that's why a lot of cybersecurity firms are really looking into this, because this really has like the potential to like destroy, I guess, cryptography. And so
would this solve like potentially be a solve to like the NP problem, those
yes.
Okay,
yeah.
so that's what would bring down the
So this is like the most
essentially.
so like this is the most like famous application, because like it can't be done on a classical computer, like literally only a quantum computer. And it just like demolishes their entire industry.
Wow. Yeah. Okay, cool, thank you.
Yeah, but those are the main applications. So go ahead, and I'm done with my presentation, but any questions, just shoot them at me. Oh, wait, I am not done, sorry. We have another demonstration. And I'm just gonna stick to this one because I can't really replicate it because it's just out of my scope. So a lot of these people, mathematicians, they create quantum algorithms. Even though we don't have quantum computers, they just go ahead and make these insane algorithms. And so this one's called Grover's algorithm. And essentially what it does is, let's say you have a database and you want to find something. You can't sort it in alphabetical order. You can't do a binary search. You just have to sort it, or you have to look through every element to see if it's there. So what this actually ends up doing is, in all those, I guess, databases of entries, so it entangles all these qubits. And so what it does is it amplifies the it amplifies, like, I guess, the item that you're looking for. So let's say you have like 1,000 lines of things you're searching for. So it slowly amplifies and amplifies and amplifies as one item until you find it. And so at the end of it, you actually get the item you're looking for. So again, classical computer, it takes big O of n to find something in a database. If you just want to search it linearly, go through every single item. On a quantum computer, it takes square root of n, which again, massive boost, because if you have 10,000 items, now you only have to query what, like 100 times. So again, quantum computing really focuses on, I guess, speed ups and the software side of things, right? Rather than trying to pack more transistors and, I guess, make hardware stuff, it really kind of focuses on utilizing the bit to its full extent and using superposition to achieve that. But yeah, that's, oh, and then running it. So we can see that it runs it. And so the number we were searching for is this one. And so it comes up with this number, and we can see that it greatly amplified. Of course, because it's a quantum computer, there's something called, again, decoherence, which makes up for all of these numbers. But the goal in the future is to kind of create less error. And again, the more times you run these, so like if you run this an infinite amount of times, this would ideally just be 100%. But if you ran it on like a simulation, which I think I did, yeah. If you run on a simulation, it's just 100% because there's no errors that you have to encounter. But yeah, questions?
I have a question.
Yeah.
So like back to the cities demonstration. What was I gonna say? Is that formula for possible routes? Is that like worst case scenario? Like you see how like it's n minus 1 factorial.
Yeah. So
over
that's how to
two?
find the number of unique routes. So
The
if you're in a city of 5,
Yeah. Yeah.
there's 12 possible unique routes, and so a regular computer has to go through every single one of these 12 routes and see which one's the most optimized.
Right.
Which like a lot of people don't need to, like if you think about like Amazon and FedEx and like UPS, like there's not 5 locations they have to go. There's like thousands per day or like hundreds. So if they really want to calculate like the most optimal route for like hundreds of cities or like hundreds of neighborhoods or like whatever you want to call it, like it's I can't even like it'd be 99 factorial, which I don't think
Over 2.
Yeah. 99 factorial is, yeah, like it's not possible for a computer to sit there and go through 9.33 times 10 to the 155th possible combinations of routes. So
Okay. And then my second. Oh.
Go ahead, Vinny.
Okay, and then my second question is, do you know about quantum supremacy?
yeah, so quantum supremacy is essentially like saying a quantum computer it works faster than a normal computer, which is like true to an extent. So like it will work faster than like for like these problems where it's literally impossible for a classical computer to simulate. But if you were to like write 5 times 3 on a quantum computer, like the classical computer is going to beat it out. So like it really depends what you're testing. So if you're testing something like this where a computer has to go through 3.11 times 10 to the 23rd operations, and a classical computer can take like the square root of that, or I mean a quantum computer can take like the square root of that, or like some insane number less, or like one of these, where the classical computer is like to the exponential and the quantum is just linear. Like obviously it's gonna beat the classical computer, but yeah, it's just like a measure of when does a quantum computer beat a classical computer in terms of speed.
That's so rad.
Thank you.
Oh, who's next?
So it's kind of like basically then like a drag race between an electrical car and like a gas car, right? Because like the gas car will win in like a longer sprint, and then the electrical car will win in the sprint. Okay.
Yeah. So I think of it as like a GPU. Like you can use it, but like you don't regularly use it. You use it for like certain problems. Like you use it heavily for gaming, but like you wouldn't use it normally for like just regular web surfing. So it's really good to like certain applications, but not others.
Wow, I don't have any other questions, but that was really rad. Does anybody else have any like questions about this? Otherwise I'll stop the recording. All right, I'm stopping the recording.